Welcome to the Explainer. Today we're going to break down the subset sum problem. Now this is a real classic, and once you get it, you unlock this super powerful pattern that you see all over computer science.
All right, let's just jump right in. The whole thing, the entire problem really just comes down to this one simple question. Say I give you a list of numbers. What are all the different sums you can possibly make with them?
So before we get into the how, let's just make sure we're totally clear on the what. What is the problem actually asking for?
Our mission, should we choose to accept it, is to find the sum for every single combination, and I mean every one. Subsets with just one number, subsets with a couple of numbers, all of them, and yeah, even the weird one, the empty set, which is basically using no numbers. And what's the sum of nothing? Well, it's 0.
Okay, let's make this real with a super simple list. 3, 1, 2. If we just do this by hand, right? First up, the empty set. That gives us a sum of 0. Easy enough. Then, we can just use one number at a time, so we get sums of 3, 1, and 2. What about pairs? Well, 3 plus 1 is 4, 3 plus 2 is 5, and 1 plus 2 gets us 3. And finally, the whole shebang. 3 plus 1 plus 2 gives us 6.
So let's lay them all out. Here's everything we just found. And hey, look at that. We can actually make the sum 3 in two different ways, from the number 3 itself and from 1 plus 2. Now if you count them all up, we have 8 possible sums. And here's where it gets really interesting. We started with 3 numbers, and we ended up with 8 combinations. What's 2 to the power of 3? It's 8. That is not a coincidence, folks. That's a massive clue.
And that clue leads us to the core idea. Doing this by hand is fine for 3 numbers, but imagine 30 numbers. It would be a nightmare. We need a system, a guaranteed way to find every combination.
So that's the real puzzle, right? How do we build an algorithm that's foolproof? We can't just stumble around and hope we find them all. Turns out the answer lies in a really simple decision that we just repeat over and over. And here it is. This is the breakthrough. For every single number in our list, one after the other, we only have 2 choices. We can pick it and add it to whatever our current sum is, or we can just not pick it and move on. That's it. A simple fork in the road for every number. Now this pick it or don't idea is perfect for visualizing. You can imagine it as a decision tree. Every choice we make splits the path in 2, and by the time you get to the bottom of the tree, you've traced out one unique subset.
Okay, let's actually walk down one of these paths together. We're at the very top of our tree, looking at the first number in our list, which is 3. Right now, our sum is 0. We haven't picked anything yet.
And boom, here's our first choice. Path number 1. We pick the 3. Our new sum is 3. Path number 2. We don't pick the 3. Our sum stays at 0. No matter which path we take, our next stop is the number 1.
Just for fun, let's see what happens if we follow the pick 3 branch. So we're one level down the tree, our running total is 3, and the next number staring us in the face is 1. And what do you know, we've got the same choice again. Do we pick the 1? If we do, our sum becomes 4. If we don't, it just stays at 3. Again, both of these new paths lead us to the next number, which is 2. Let's keep going down the pick route. We chose to pick the 1, so our sum is now 4. And we've finally reached the last number in our list, the number 2. Okay, one last decision to make. We can pick the 2, which gives us a final sum of 6, or we can skip it, leaving our final sum at 4. And since that's the end of our list, we're done. These are 2 of our final answers. So you can see how that one specific path, where we decided pick 3, then pick 1, and finally pick 2, led us directly to the subset sum of 6. And here is the absolute beauty of it. If we just systematically explore every single branch of this tree, every left turn and every right turn at every level, we are mathematically guaranteed to find all 8 possible sums. We won't miss a single one. That's our algorithm. What's so cool about this is that the logic of our decision tree maps perfectly onto a really elegant coding concept called recursion. We can write a function that basically just walks down this tree for us.
Any good recursive function needs 2 key parts. First, a base case, a condition to stop. For us, that's when we run out of numbers to look at. At that point, we've found a sum, so we save it. The second part is the recursive step. And what is that? It's our 2 choices. We just have the function call itself twice. One call for the pick scenario, and another call for the don't pick scenario.
This is pretty much what that pick choice looks like in code. We just say, hey,
call the solve function again, but this time move to the next number in the list and, oh yeah, add the current number's value to the sum before you go.
And the don't pick call is almost the same. We still say move on to the next number, but this time we just pass the sum along exactly as it is. Nothing changes. These two simple lines of code are the engine that drives the whole thing.
Now, this recursive approach is, you have to admit, pretty slick. But with any algorithm, we have to ask about performance. What's the cost of exploring this entire ever-expanding tree? Well, since we make two choices for each of the n numbers in our list, the problem size doubles at every level. This gives us what's called exponential time complexity, or O of 2 to the n. And it's the same for space. Why? Because we ultimately have to store 2 to the power of n different sums in our final answer. It's elegant, but it can get slow and memory-hungry pretty fast.
And that really brings us to the big takeaway here. This idea, this simple pick it or don't pick it pattern is way bigger than just this one problem. It's a fundamental recursive technique you can use to solve a whole class of problems, from generating all possible combinations of things to figuring out the most valuable items to stuff in a backpack. So the real question is, now that you know this pattern, what other tough problems out there can be cracked with this same simple choice?